we were discussing that this quantization process is basically the process of mapping from
Sir,
the
can you
real
zoom in,
line.
please?
Yeah, just a second. So now is it okay?
Yes, sir.
Yeah. So we had talked about this, and we had said that we want to minimize the quantity right, which corresponds to the mean squared quantization error. And we had given justification that this is equal to the basically the power of the error, and we want to minimize the error power, so we want to minimize this. Fine. Now, sorry, x tilde. Not this. Now let us try to minimize this. For that, I have to first write this out. So expectation of, now we know that the real line, or simply the range of xn is part is to be partitioned so let's call this function as j, is to be partitioned, excuse the spelling, such that expectation of, oh cool, the laptop is back. So let's switch to the laptop, and yes, we know that the real line, or simply the range of x, is to be partitioned such that expectation of minimized. So xn, right, and q of xn is, or q of xn is this b, such that whenever x of n is in the partition ai, q of xn right? This is okay from yesterday's discussion.
Yes, sir.
Yeah. So therefore, for x in AI, xn or xn in AI, for xn in AI, x tilde of n equals xn minus bi, right?
Yes,
Therefore, expectation of x tilde n equals x in AI, probability x in AI times xn minus, or xn in AI minus, see if this works. Yeah, this works. X minus right. This is right. Anyone having any problems with this? Great. So assuming that we agree on this, J equals summation.
so your screen is actually stuck on expectation external. Oh, okay, now it is visible.
Okay, yeah. So now look at it if it is okay. Fine. Now the quantization problem. Problem is to choose the sets AI and, or choose the sets AI and B such that J is fine. The,
Sir, the
the
sum is over. The sum is over
sorry,
different
this sum
AI.
is over. Sorry, this sum is over. My apologies. Actually, this should be this, or rather, let's rewrite this entire thing. Expectation of x tilde n whole square equals summation I equal to 1 to n PR, my, yeah, expectation of x minus bi whole square given x in ai. This thing. Yeah, I'm sorry about that. Fine. So the laptop was misbehaving and I got confused while writing this. Now is it okay?
Can you explain the expectation part, the right hand side equation?
Yes. So what happens is that mm, my laptop is slightly misbehaving today. This part is okay.
Yes, sir.
Yeah. So now expectation of x tilde n whole square can be written as summation I equal to 1 to n probability I probability x ai expectation of x tilde n
Sir, in the right hand side, there's an expectation because x is a continuous
of
random variable.
yes. So in general, yes, x is a continuous random variable, and in general, you can write probability of, or rather, for any random variable. I'm just doing a general thing. Say x is a random variable, then expectation of x equals probability of x greater than 0 times expectation of x given x greater than 0
Okay,
plus
sir.
probability of x less than equal to 0 expectation of x given x less than equal to 0. Right?
Okay,
This is
sir.
okay.
Yes, sir. Yes, sir.
So this way I can partition the real line into n partitions and write it like x in ai. Right? Now for x in ai, x tilde n equals x minus bi, right?
Right? Yes, sir.
So based on that, we get this j. And the quantization problem, I'll restate it. Quantization problem is solving for ai, the partitions of the real line, and bi, that the error is minimized. Fine. You have to find these AIs and BIs so that the error is, mean squared error is minimized.
Yes, sir.
So the question is that you have to break it into n parts so that this error is minimized. And now this problem is impossible to solve if you try to optimize for both AI and BI simultaneously. So what we do is we either solve this for BI given the partitions or given BI's the reconstruction levels. We call these reconstruction levels. We solve this for AI. Fine. So let's say we first try to solve this given AIs. Set partitions. We want to know what are the for that. If we look at this expression, then okay, I'll write it again. This guy is really slow today. J equals summation I equal to 1 to n probability x in AI expectation of x given bi minus bi given x. Fine. This beast.
Yes, sir.
So now the good thing is that so all of these are non-negative quantities. Fine. All of us agree that these are non-negative quantities.
Yes, sir.
So since all of these are non-negative quantities, minimizing the sum their weighted sum will be the same as minimizing these individually, right? Minimizing the weighted sum will
Yes,
be the
sir.
same as minimizing these individually, or so we want instead of minimizing this sum, what we have reduced our minimization problem to is given AI minimize expectation of x minus or minimize over bi expectation of x minus bi whole square x. So we know that x is in AI, so I remove this. Fine. And this all of us
Yes,
know
sir.
will be minimized when bi equals expectation of x given x in. Right? This is known, or should I prove this?
Like in
So this
quadratic
is simply the mean
differentiate, we
of
get the
bi.
average. Like that's the thing.
Yes. Yeah.
Yeah. Okay.
So that's the way that build a quadratic, take the expectation, differentiate it, and you'll get this. So I'll assume that this is done. So these BIs, given AIs, BIs can be found like this, and given BIs or given the centers, we want to find AI such that again sorry, summation I equal to 1 to n x in AI x minus bi whole square given x in AI. So again, we want to do the same thing, right? Now, simply for a given bi want to choose the points such that probability x given AI expectation of, or not expectation, we want to choose the probabilities that or we want to choose AI such that x minus bi whole squared is minimized for all x in AI. Right? We would want to choose. So these AIs are collections of X, or AIs are subsets of the real line. So AIs are sets. So we want to make these sets such that this distance for all X in AI, this distance is minimized. Uh, this quantity is minimized. When we define Euclidean distance in the next semester, this will become clearer. But this is what is the nearest neighbor approach, that we want to choose the points that are closest to BIs. So in each set, we choose the points that are closest to BIs, and for each so for each set we choose the points that are closest to BI, and for each set that is given, we want to we choose the BIs as the centroids of those sets. So this is done
Sir,
iteratively to get the optimal quantizer. Yes, Adit.
sir, but in the previous thing, when we were trying to choose a BI, we could do it individually. But can we do that individually? Because once we choose a AI, that affects the other, I mean, the neighboring AI minus one and AI plus one, right?
Yeah, so you assign each point on the real line to an AI.
Okay.
Okay, so what you are doing is you are choosing AIs and BIs, and here you are assigning each point on the real line to an AI, and you choose the AI for which this quantity is minimized for a given BI.
And sir, how do we know when we are iterating that we have reached a minimum?
This algorithm thankfully converges. So this is known as the Lloyd Max algorithm or Lloyd's optimal quantizer. Today, yeah. What? My laptop is misbehaving more than usual. This is a Lloyd Max quantizer, and generally it doesn't get stuck in local minima. So this is an iterative algorithm, and generally it converges. And for those interested in machine learning, this is also the k-means or k nearest you have heard of k nearest neighbors or k-means, right?
Yes, sir.
Yes, sir.
Yeah, this is that algorithm, or this is the theoretical idea behind that algorithm. If you do it for vectors, this is for scalars. We'll do it for vectors in the next semester. So now, all in all, this quantizer is optimal, but is hard to bring down to practice. So this is the optimal quantizer, but this is hard to bring down to practice. So what we instead do is practically we use uniform quantization. That is, given that the input signal takes values between A and B, we divide the range into L equal levels, or rather not, because I've used A and B, let's use, say, what should we use? M. Even simpler, minus M and M. We divide the range into L equal intervals that each interval is of length 2m divided by L. Fine. So we
Yes,
divide
sir.
it in, so we call this delta is the quantization step size, and delta equals 2m over L. For this, we assume the step size to be small enough so that the signal can be assumed to be uniformly distributed in the Fine. So AIs in this case are minus infinity minus m plus delta by 2 minus m plus delta by 2 to minus m plus 3 delta by 2 all the way up to m minus delta by 2 to and the reconstruction levels minus m plus delta m minus delta. Fine. You can also have it other way. You can keep the boundaries at minus infinity to minus m minus and so on, and the reconstruction levels at the midpoints. It all depends. So if the signal is bounded between minus m and m, then the optimality would ask you, then you would want that say if we know the signal to be strictly bounded in then AIs minus m to minus m plus delta m minus delta. Fine. These and fine. These arguments sound right?
Yes, sir.
Yeah.
Yes, sir.
So this quantizer, this uniform quantizer also comes in two flavors. This is called the x q of x mid-rise quantizer and x q of x mid-thread quantizer. Can you guys spot the difference? So this has an even number of, the mid-rise quantizer has even number of levels. This has an odd number of levels. The difference being that here the levels are at minus delta by 2 and delta by 2. These are the reconstruction levels. And here there's a reconstruction level at 0. Fine. So this is more symmetric, the mid-rise quantizer, but practically we use the mid-thread quantizer for speech signals. Why would be that? Any guesses? For speech, the mid-thread quantizer is more popular than a mid-rise quantizer. Any guesses why?
So mid-rise is like the floor function which we use in like any programming language. So that would be
No. This is not like the floor function. This is always the round function. Oh, sorry. The problem is with my placement of the axis.
Okay.
No, this is not the placement of the axis. So at 0, it transitions from minus half to half. This is right.
Yeah. So basically, this in
This is not
mid-rise
the floor function. So a floor function would have transitioned, would have stayed at 0.
No, like what I meant is these transit like here the transition happens at whole number. Here it happens at half, like the fraction.
So yeah, so the
So
nice thing
that
is that all of these are all these deltas are reals. So you can take delta to be pi. It never would be whole number.
no, I meant the like usually the better approximation would be like a 0.5, say next 0.5. Like if we consider the middle number as a whole number, that would be a better approximation.
No, both of these are equally good approximations.
Okay.
Okay, actually, we'll go on to prove that the mid-rise quantizer is marginally better in terms of the mean squared error than the mid-thread quantizer. The thing is that there's a quantization level at 0. So speech, most of speech, which is the most common form of communication signal, has a lot of what do you say? A lot of quiet periods. When I'm talking to someone, not in a class, but when I'm talking to someone, most of my speech is 0 or 40. I'm silent 60% of the time, talking 40% of the time. That is practically observed. And in any case, you would see that when you're talking to someone on an average, you would expect that you are silent 50% of the time. Right. So if you use the mid-rise quantizer, that 50% of the time you will be sending either plus delta or minus delta, depending on the acoustic noise, which will amount to some power, but at the receiver. But if you use the mid-thread quantizer, you will be sending a plain 0, which means that there's a silent period. So silence periods are easier to detect in mid-thread quantizers. That's why we use the mid-thread quantizer. Fine.
Okay, sir.
Yeah, great. So this is the mid-rise quantizer and this is the mid-thread quantizer. And yes, so now let's say the next thing that we would be interested in is the loss or the error power. So assuming the signal to be uniformly distributed between -m and m, and also having power cm square. You can say that if it is uniformly distributed between -m and m, the power would be m square by 12. But I'm discounting that and saying that it assume that it has a power cm square. C is some constant. not necessarily, it's approximately uniform. So let's say this is some multiplying constant. Then within each step, the quantization error x delta n, x tilde n is also uniformly distributed, right? Makes sense?
Yes.
So x tilde n equals, or x tilde, one upon delta for all the intervals. Okay. And therefore expectation of given x in ai equals basically bi minus delta by 2 to bi plus delta by 2 x minus bi whole square dx, right?
Sure, into 1 by delta.
Yeah, into 1 by delta. My apologies. Into 1, right? Great. So
Yes, sir.
now if we subtract bi from everything, nothing will change. I subtract, let's say I say q equals to x minus bi. Nothing will change. 1 upon delta minus delta by 2 to delta by 2 q square dq. Fine. Equals 1 upon delta q cube divided by 3 minus delta by 2 to delta by 2 equals 1 upon delta 1 upon 3 delta actually, delta cube by 8 plus delta square by, sorry, fine.
So we are taking the case, or
Huh?
we are taking the mid thread or mid.
General, any quantizer, any uniform quantizer, this will be true.
Okay, sir.
Okay, because even in a mid-thread quantizer, from minus delta by 2 to delta by 2, you will place everything to, you'll move everything to 0.
Oh, so only the BIs will change in that case.
Yeah, only the BIs will change. So any uniform quantizer, this will be true. Fine. And so expectation of x tilde n square equals summation I equal to 1 to n probability x in ai delta square by 12. Fine.
Yes, sir.
Equals, this is 1.
Yes, sir.
So the quantization noise power. We call this we quantize, since this quantization error acts as a noise, we call this quantization noise. Quantization noise power equals delta square by 12. Signal power equals Cm square, but delta equals 2m divided by L. Fine. Delta equals 2m divided by L. We had talked about this earlier. So
Yes, sir.
signal to quantization noise ratio, call this SQNR, is Cm square divided by 2m by L whole square divided by 12 equals 12 Cm square divided by 4m square by L equals L. M squared cancels 4, 3, 3Cl square. Fine.
Yes, sir.
Yes, sir.
Or in other words, the larger the number of quantization levels, the more will be the signal to quantization noise ratio, which makes intuitive sense.
Yes, sir.
Right? But picture abhi baki hai mere dost. So, but
Sir, also can we say that the more the power of the signal, the better is the that is also obvious only.
yeah,
Okay.
that disappears. That's the beauty. It only depends, the signal to quantization noise ratio depends only on the number of quantization levels if you calibrate it to the power accurately. That's the beauty of this thing. But after quantization, we have to send this as a digital signal in the form of bits, right? We have to send everything in the form of bits at the end of the day, zeros or ones. Agreed?
Yes, sir.
A digital
Yes, sir.
medium, a digital logic cannot take these quantization levels. So if we represent each quantization level with R bits, then so you can represent these quantization level with R bit, these quantization levels with R bits. So then there can be L equal to 2 to the power R quantization levels, right?
Yes, sir.
So this 2 to the power R is not, yeah, L equal to 2 to the power R quantization levels. And consequently, L equals 2 to the power R and SQNR equals 3C 2 to the power 2R. Now, all of us are too accustomed to uh, write everything in terms of uh, so all the signal to noise ratios we are accustomed to writing in dB. So SQNR in dB equals 10 log 10 3C to the power 2 to the power 2r. Fine. 10 log 10 3c plus 20 log 10 to the power r. Fine.
Yes, sir.
So depending on c, this can be some k equals 20 log 10 to the power 2r or 20r actually 20r log 10 to the power 2 plus k. But we know that log to the power this approximately equals 3. Right?
Sir, 3 or 1/3?
Sorry.
Minus 3.
0.3. My apologies. 0.3. I multiplied that 10 as well. This is 0.3. I'll tell you the exact value. So as a scientific calculator, so 2 log. So 0.3010, which is approximately 3, equals 0.3, and therefore 20 log 2 is 6. 6r plus some k. Or as a rule of thumb, you can say that the signal to quantization noise ratio for an R bit quantizer approximately varies as 6r plus k, where k depends on where k is a factor of the or k is a relation between the signal power and the signal amplitude. Fine.
Yes, sir.
Great. So you have a class at 4, right?
Yes, sir.
So let's stop here and we'll finish quantization on Tuesday. So Tuesday, I hope you remember that I have another engagement from 2 to 3:30. So we'll start at 4.
Okay, sir.
Okay, great. Bye.
Bye, sir.